Hi, everybody. Welcome back to Introduction to Physics, Lesson 13. So today we're going to be doing a few more examples about how to apply Newton's laws of motion in different scenarios. But this time we're also going to incorporate friction and see how that changes the math behind some of these things. So we didn't quite finish yesterday's notes, so we'll go ahead and start there, talking about apparent weightlessness, and then we'll move into friction. All right. So apparent weight and weightlessness. So apparent weight is the upward force or the normal force, that kind of reaction force that opposes gravity. And that's what prevents an object from falling through a surface. So that could be provided by the floor, the table, the ground, something like that. So it's actually that upward force that we feel against our feet holding us up that's preventing us from falling down due to gravity. So when you're stepping on a scale to get your weight, what you're actually getting is your apparent weight. The amount of force that the scale is applying to hold you up, that's the apparent weight. And it's that weight that we measure when we see how much we weigh, which is kind of interesting, I think. So usually your apparent weight is equal to your actual weight, except in the case where you're accelerating vertically, so your motion is changing vertically, like in an elevator or a rocket or a roller coaster, on a swing, anything like that, where your motion is changing vertically, then your apparent weight will not actually equal your actual weight. So this can also be different from each other if there's another force other than gravity and the normal force that's acting on the object. For example, when you go swimming and you're in water, you have a buoyant force as well that's kind of holding you up. And that's different than a normal force or a surface force. So in that case, your apparent weight would not be equal to your actual weight or the actual force of gravity that's pulling you down. Magnetism can affect this. Centrifugal force, so if you're going on like a really spinny ride, like um, I don't know, I mean, Ferris wheels don't go super fast, but still in a Ferris wheel, you can kind of feel like you're being pushed out of a circle a little bit. And so that will change the apparent weight that you feel. If there's another object that's exerting a gravitational force on you as well, that will change your apparent weight compared to your actual weight too. Weightlessness is what happens when there are no contact forces that are pushing up on you. So in that case, your apparent weight is equal to zero. And this would be the case for astronauts in space. There is gravity in space, right? That's one of the big misconceptions that we've talked about before. There is gravity on space. So there is gravity pulling on those astronauts in the International Space Station. But when they're in the International Space Station, the space station is also orbiting around the Earth at the same speed that they are orbiting around the Earth. And so it feels like they're weightless because there's no force necessarily like holding them up. So that would be an example of apparent weightlessness. You can also kind of feel this when you're at the peak of a swing. Like if you're swinging really high, right at the peak before you change direction, either way, going forward or going back, you kind of feel a little like, I don't know, like a jolt in your stomach of like, "Ah, I'm floating, just really briefly. That would be weightlessness because the seat of the swing is no longer technically holding you up. Um, and so we don't have that contact force, that normal force pushing on us as well. So, two different interesting cases that you can feel, you know, in your daily life. I mean, I guess I don't know how often you go on swings or like weigh yourself in an elevator, but these are things that you could experience in your day to day life. So, we're going to do a couple quick examples with apparent weight. And in this case, we have a woman standing on a scale in an elevator. Now, again, I don't know how often you would do this particular thing in everyday life, but I mean, you do you. So this elevator is accelerating, excuse me, at 2 meters per second squared. What is the reading on the scale? Okay, now here's the woman in this elevator, and if you've ever been in an elevator, you've probably experienced this sensation before, where when you're going up in the elevator, you feel like you weigh a little bit more at first. Or if you go down in an elevator, you feel like you're, I don't know, a little less heavy on pushing down on the floor. So we're going to see how much this actually affects you mathematically. So here's our woman. We know we have her weight, the force of gravity pulling down. That's always equal to mass times g. So 50 kilograms times 9.8 meters per second squared is 490 newtons downward. We have this normal force supporting her, right? That's the scale holding her up. So you need to figure out what that normal force is. And in this case, since there is an acceleration to this elevator, these two forces are not going to be equal to each other. So in the y direction, since we don't have any forces in the x direction, we have the normal force pointing up, so that's positive, minus the force of gravity pulling down, minus because it's down, negative, and that equals the mass times the y acceleration. So our normal force then, if we take the force of gravity and move it over to the other side of the equation, the normal force equals the force of gravity, mg, plus the mass times the acceleration in the y direction. So we can group like variables together. There's a mass in both of those terms, so we'll pull that outside the parentheses. And so we get mass times g plus a. And that gives her a normal force or an apparent weight of 590 newtons. Now, again, does this answer make sense? Well, think about your own experience riding in an elevator. Since this elevator is accelerating in a positive direction, that would mean the floor is pushing up on her harder to make her move upward. And so we get a bigger normal force than we would normally. Now, on the flip side, and I want you to give this one a try yourself really quickly. Now the elevator is accelerating at negative 2 meters per second squared. So how will that affect the reading on the scale? Again, you should know just kind of from your own experience whether this answer is going to be bigger or smaller than the previous answer. But take a minute, kind of go through those same steps that we did just a second ago in the first part of this example and see if you can set up this problem. I'll give you a minute or two to think about it. All right, I know that was a pretty quick minute. You'll find as we go through this together that it's very similar to what we just did, except now our acceleration is in the opposite direction, and so we're dealing with the opposite sign. Okay, we're still going to start off with our free body diagram, showing all of the forces acting on this lady. So again, we have her weight pushing down. The weight is the same as previously because her mass stayed the same and the acceleration due to gravity stayed the same. So no change there. Okay, again, we need to find what that normal force is to know what her apparent weight is. So still no forces to deal with in the x direction, just the y direction. The problem starts the same way, right? The sum of the forces in the y direction is the positive normal force minus the downward force of gravity equals mass times our acceleration. Okay, so again, once we take our force of gravity and move it over to the other side of the equation, we get the same setup that we had before, right? We've taken out the mass because that's common in both terms, and now we have mass times g plus a. except now A is negative. Right? And so when we do this math, we'll find that she ends up with a smaller normal force or a smaller apparent weight when the elevator starts accelerating downward. Hopefully that makes sense to you guys, because again, hopefully this is something that you've experienced firsthand, even if you didn't have a scale. All right, so here we go, diving into friction now and how this will affect our problems. So friction, as we talked about last week, is always opposite the direction of motion. So it can seem weird sometimes, and we'll go through some examples where we deal with friction and things on angles and stuff. But whenever you have an object that's sliding on a surface, friction is going to act in the direction that opposes how that object is moving. And remember, air resistance is a form of friction as well. So there are two kinds of friction. The first kind of friction is called static friction. And so this would be before the object starts moving. So sometimes this force is referred to as a smart force, because it's always just enough to stop something from moving as long as that is within a certain threshold. Once it reaches that certain amount, that magical number, then the object will start sliding. But let's say you're like trying to push a really heavy filing cabinet or whatever. You can push with a little bit of force, it's not going to move. You can push with a medium amount of force, the friction force is going to be just enough to stop that motion until you're pushing at just the right force that will make this equation no longer true, really. You're pushing with a bigger force than um, this inequality, and so then the object will start moving. So this equation for static friction, again, remember friction is a lowercase f as an abbreviation. So static friction is F with a little s. And this is always going to be less than or equal to this coefficient of friction, mu. So this symbol, this is a Greek letter, mu. And this is the coefficient of static friction. So it gets a mu s times the normal force. So again, mu is that coefficient of friction. I mentioned briefly last week that this is a number between 0 and 1. Usually it is possible for it to be bigger than 1. And that would be, well, I'll hold that thought for a moment. But usually it's a number between 0 and 1, which corresponds to how slippery the surfaces are against each other. So if it's more slippery and you have a smaller coefficient, it will be closer to 0. Now, things like ice, skates on ice are very, very slippery, so they have a very small coefficient. But if you can imagine something like Velcro, right? If you've ever tried to like rub Velcro across itself, it really does not go anywhere. I mean, that's like the whole point of Velcro is to stick things together. So if you have these two sides of Velcro, and again, I don't have anything Velcro around me, unfortunately, but if you have these two sides of Velcro and they're stuck together and you try to slide them, it's not going to work. It would be much easier to just pull them apart and move it physically than it would be to try to slide it across itself. So that would be a case where the coefficient of friction is bigger than 1. If it's easier to just pick it up and move it and then just slide it. But that's kind of a special case. Usually we don't get things like that happening. The second kind of friction is called kinetic friction. So that's when the object is moving. Kinetic means motion, and static kind of means stationary. So kinetic friction happens when an object is already sliding across a surface. And this is always going to be the same value for a given set of surfaces against each other. So you'll have the same coefficients um, for any two materials against each other. Those numbers are going to be set the whole time. The equation you can see is very similar to the equation for static friction. We have a subscript K now because we're dealing with kinetic friction. And in this case, it is equal as opposed to less than or equal to. Okay, that force of friction is going to be the same no matter how fast it's moving or how strong you are pushing. That force of kinetic friction is always going to be the same for a given set of surfaces. So these coefficients that I keep referring to are just numbers that you can look up in a table in your textbook or on the internet. Um, Again, these are set values for set combinations of surfaces. So usually we'll see, and I'll show you some examples, but usually we'll see that the static coefficient is bigger than the kinetic coefficient. And that really kind of ties back into our understanding of Newton's first law, that it's harder to make something start moving than it is to to keep an already moving object moving, right? That's inertia, the tendency of an object to resist changing its motion. So if something is stopped, it's hard to make it start moving. But if it's already moving, then it's not as hard to keep it moving, usually. So we can see here, like even though these two surfaces seem fairly smooth against each other, the surfaces of materials on the microscopic level are actually very rough against each other. And so that's why we get friction in the first place, is because these rough surfaces that we might not be able to see are rough, they're kind of grating along each other. So that's really what friction is caused by. Here are some examples of coefficients of friction. So you can see in each case, except for Teflon, on Teflon, the static friction coefficient is larger than the kinetic friction coefficient. In the case of Teflon on Teflon, they are the same. And Teflon on Teflon was made to be a rather frictionless surface. But you can see, like our joints, if your joints are functioning correctly, they have a very, very low coefficient of friction. So there's hardly any friction in the joints of your body. So that would be like your shoulders or your knees, your elbows, those sorts of things, which I think is really cool. Um, and you can see here too, like rubber on concrete, when it's dry, has a very different set of values than rubber on concrete when it's wet. All right, so you can really see the effect that wetness has on these coefficients of friction. Okay, so here's an example with friction. A 3 kilogram book sits on a table. The coefficient of static friction between the book and the table is 0.25. The coefficient of kinetic friction between the book and the table is 0.15. How much force is necessary to start the book moving from rest? So, which kind of friction are we going to be dealing with in this case? Well, the book is at rest now, and we want to know how much force is required to make it start moving. So we're going to be dealing with static friction here. Okay, let's draw our picture. Here's the table and the book. We know its mass is 3 kilograms, and we're pushing on the book. How much force is necessary to start the book moving? So some applied force in this case. Okay, there we have our two coefficients of friction that were given to us. And now let's draw a free body diagram. So we always have the force of gravity pulling down towards the center of the earth. And that again is mass times g. We're going to have a normal force pushing up. And in this case, those two forces are equal to each other in magnitude because this book is not falling through the table, it's not being launched into the air. So we don't have an acceleration in the y direction. these two forces are balanced. We do have an applied force to the right, and we also have some amount of static friction to the left. Again, remember, friction opposes the direction of motion. So if this book would start sliding to the right from our rightward force, then friction points back to the left, opposing that force. So in order to start moving, we need to overcome this static friction. We need to get past that threshold and make it start moving. Once we get static friction up to the limit, then it will move. So our coefficient of static friction here is 0.25. The normal force, since it's equal to the force of gravity here, those two forces are balanced, then we can just plug in m times g for our normal force as well as for gravity. So once we plug in all of our numbers, we'll see that the force of static friction is going to be less than or equal to 0.25, our coefficient, times the mass, 3 kilograms, times g, 9.8 meters per second squared, or 7.35 newtons. Right, so once we hit a applied force of 7.35 newtons, if we go beyond that amount of force, then the book is going to start moving. Okay, so now if we push with 7.35 newtons of force, what is its acceleration? So our free body diagram here looks very similar, except now since we're dealing with a, a sliding book, our static friction has been replaced with kinetic friction, but all the other forces are in the same place, same label. So now the sum of the forces in the x direction equals mass times acceleration in the x direction, Newton's second law, right? And again, we're not dealing with acceleration in the y direction. There's no change in motion in that direction, so we'll just ignore that. Our sum of the forces is this positive or rightward applied force minus this leftward kinetic friction force. And again, that equals mass times acceleration. So if our applied force is 7.35 newtons and our force of kinetic friction is the coefficient times the normal force, then we can plug in the numbers that we're given. The coefficient of kinetic friction is 0.15, mass 3 kilograms, g 9.8 meters per second squared. Again, our mass is 3 kilograms, and now we're trying to find that acceleration. So typing all that in our calculator, dividing both sides by 3 gives us an acceleration of 0.98 meters per second squared. Again, that's our x acceleration. And as I said before, our y acceleration is 0. All right. Example 11. You are pushing a heavy box across the carpet. Okay, carpet, rough surface implies friction. The box has a mass of 30 kilograms. You push at a 30-degree angle downward to push the box. The coefficient of kinetic friction is 0.4, and you push the box at a constant speed. Now, there are some really important key words and phrases in there for you. I identified one, carpet, rough implies friction, and then they specifically told you there's kinetic friction. But I have a couple of questions to help you set up this problem in your mind before we do the math together. So, first question, what is the net force on this box? Take a second. Net force. Okay. There's a key phrase in here that will help us figure that out, and it's right there at the very end. Constant speed. So if we're pushing it with a constant speed, constant velocity in one direction, we're pushing it in one direction. So constant speed, well, that means there's no change in its motion. There's no acceleration. So the net force is 0. in both directions. Next question, is the normal force on the box equal to mass times g this time? Hmm. Well, no, it's not, right? Because we have this additional force that we're pushing with, and that's at a downward 30-degree angle. So since we're additionally pushing this box down and there's a force of gravity pulling down, that means the normal force is going to be equal to not only the force of gravity, but the force of gravity plus whatever this y component of our force ends up being. And lastly, draw a free body diagram for this scenario. So really quickly, try to sketch that in your mind before we draw it out together. All right, how many forces did you come up with? Let's see if you got it right. Okay, so the question is asking what is the applied force? Here's our scenario, right? We have this box sitting on the carpet. We have our kinetic friction coefficient of 0.4. We're pushing at a downward 30-degree angle on this box. So that would be our applied force. Okay, so free body diagram. We have the force of gravity pulling down, the normal force pushing up. They are not equal to each other because we have this applied force at a downward 30-degree angle. And we also have friction, kinetic friction, because this box is going to be sliding. Okay, so here's our free body diagram. Woohoo! Hopefully you got that right. So looking at our x direction, because that's really where the acceleration is going to be happening, the sum of our forces in the x direction is that x component of the applied force minus the force of kinetic friction, and that equals mass times acceleration in the x direction. So since our x component is the side of the triangle that's adjacent to the angle, we'll use the cosine. So the applied force times the cosine of our angle 30 minus, and the equation for kinetic friction is the coefficient times the normal force, equals mass times acceleration in the x direction. But we were told this is moving at a constant speed, so there's no acceleration in the x direction. That means that our applied force times the cosine of 30 equals our kinetic friction. In the y direction, now we're summing the forces in the y direction. So we have the normal force pushing up minus gravity pulling down minus this y component of the applied force equals our mass times acceleration in the y direction. And again, it's not accelerating in the y direction. So that's going to equal 0. But we have the normal force minus mg minus the applied force times the sine of 30, because this y component is the side of the triangle opposite the angle. So our normal force here, rearranging this equation, is mg plus fa sine 30. Right? We took both of those minus chunks, moved them over to the other side of the equation, and they became positive. So now that we know what the normal force is, kind of, we have an expression for it, we can plug that into our result for the x component. So from the x component, FA cosine 30 equals mu k times the normal force, which we know is mg plus FA sine 30. So simplifying this and plugging in the numbers that we know, the cosine of 30 degrees is 0.866. Our coefficient of kinetic friction is 0.4. Mass times g, 30 kilograms times 9.8. And our applied force times the sine of 30 gives us an applied force of 177 newtons. Okay, so we can see how friction um, does kind of complicate things in these scenarios, but it's not impossible to deal with. Okay, so conceptual question for you guys then. When you are pushing a heavy box across the carpet, do you want to push down harder or do you want to lift the box up a little bit? Well, if we're trying to minimize friction here, we would lift it up a little bit. Remember, friction depends on the normal force or that supporting force from the floor. So if we're trying to decrease the friction, then we need to decrease the normal force. And that would involve lifting it up a little bit. All right, we're going to do another couple examples with these Atwood machines that we mentioned yesterday. The first one is going to be without friction, and then the second part of this is with friction, and we'll see how that affects things. So in this case, a block rests on a table connected to a hanging block on a pulley. The block on the table is 4 kilograms, and the hanging one is 7 kilograms. What is the acceleration if there's no friction? So yesterday we dealt with an Atwood machine that had two hanging blocks suspended over a pulley. And this case is a little bit different. Now one of these blocks is sitting on a table, but there's still a hanging block. So we're going to assume that there's no friction here between mass 1 and the table, and so it can slide freely as this one falls down. So since we have two objects, we're going to draw two free body diagrams. For the first mass, we have the force of gravity pulling down, the normal force pointing up. Those two forces are equal to each other in magnitude because there's no acceleration of this block vertically. There's also the tension force from that string that's connecting the blocks, and that is to the right. We're not dealing with friction this time, so we're not going to draw friction to the left. This second block also has tension from this string, this time pointing up, and it has the force of gravity pulling down. No X forces to deal with for the second block. So when we're thinking about what the acceleration is, we have to remember that these two blocks are connected to each other. And we weren't told necessarily, but we'll assume that this string does not stretch. It's not like a slinky or something crazy like that. So this string is going to stay tight and not stretch. So the acceleration that one block experiences is the same acceleration that the other block experiences. They'll move at the same time and with the same acceleration. So anywhere we see an acceleration in this problem, I'll just plug in the variable a because it will be the same acceleration for both blocks. So for our first mass, this mass is going to move in the x direction. So that's the direction that we'll consider. The sum of our forces in the x direction is just tension, and that equals the mass of that block times its acceleration, which is the same as the second block's acceleration. For mass 2, this one's moving in the y direction. So the sum of the forces in the y direction is tension upward minus the force of gravity downward, and that equals negative mass 2 times acceleration. Again, that acceleration is negative because it's downward, we're assuming, and so that would be in the negative direction. So up here in this first expression, we have an expression now for tension. So we can take that and plug it into our result for the second block. So instead of having tension minus M2G, now we have M1A minus M2G equals negative M2A. We can see that two of these terms have an acceleration in them, two of them have M2 in it, but since we're looking for the acceleration, we want to group our terms so that we can get acceleration as a variable by itself. So I'll move m2, this negative m2a, to the other side of the equal sign. And I'll move this negative m2g to the other side of the equal sign. And when we do that, both of them become positive. So now we can factor out the a, and we get a times m1 plus m2 equals m2g. Divide both sides by m1 plus m2, and that gives us our equation for acceleration. Now we can plug in the numbers that we know. M2 is 7 kilograms, M1 is 4 kilograms, G is 9.8 meters per second squared. That gives us an acceleration of 6.27 meters per second. Now let's ask ourselves just really quickly, does this make sense? Well, let's take a look at our equation that we came up with. If mass 2 is 0, then we get 0 times g, which is 0. So there would be no acceleration. And that makes sense. If there's no hanging weight here, then there's nothing to pull this other block off the table, right? So it wouldn't move anywhere. So our acceleration being 0, if m2 is 0, that checks out. If mass 1 is 0, then we get m2 divided by m2, which is 1 times g. So our acceleration would equal acceleration due to gravity, and this block would be in free fall. Well, that checks out too, because if this block weren't there, if its mass were 0, then there would be nothing to slow down block two's fall, and it would fall, well, it would be in free fall, right? So both of those scenarios check out. This equation makes sense. Our answer, therefore, seems highly reasonable. If there is friction, right, so now we're dealing with this case, if the kinetic friction coefficient equals 0.3, that's going to change our scenario a little bit. So it won't necessarily change any of the forces that we had from before, but now we have this leftward kinetic friction force on just block 1. So now for block 1 in the x direction, when we sum those forces, we have tension, which is positive, minus friction, which is negative. And so tension minus the coefficient times the normal force. Well, our normal force in this case is equal to the force of gravity, m1 times g. And according to Newton's second law, that equals mass 1 times acceleration. So trying to get an equation for just tension by itself, we get tension equals m1a plus mu m1g. Right, we took this chunk, moved it over to the other side of the equals, and it became positive. For m2, again, there's no motion in the x direction, so we're just dealing with the y direction. And again, we have tension pulling up and force of gravity pulling down. That equals negative m2a, negative because this block is going to be falling downward. So we'll plug our expression for tension into our result for m2. There it is. We can try to group these like terms together. Again, because we're looking for the acceleration, we're going to try to get all of the acceleration terms together. So we'll take this negative m2a from the right side, move it over to the left, it becomes positive. And then these other terms that don't have acceleration will move over to the right side and switch their signs. So factoring out our acceleration, just like we did before, gives us m1 plus m2 times a. Here we can factor out a g because it's common in both terms. So g times m2 minus mu k m1. And now we divide both sides by m1 plus m2 to get this gross looking expression. So again, you can go through the same kind of logic. Does this equation make sense? What happens if m2 is 0? What happens if m1 is 0? What happens if those two masses are equal to each other? go through that same kind of thought process to see if this equation makes sense. But here we'll plug in our numbers. So M2 is 7 kilograms. Our coefficient we were given is 0.3. M1 is 4 kilograms, and G is 9.8. So that gives us an acceleration of 5.17 meters per second squared. So friction literally says not so fast in this, well, in anything that it affects. And so we can see it's actually slowed down the block's progress forward, um, comparing 6.27 meters per second squared without friction to 5.17 meters per second squared with friction. And zero point 0.3 is a fairly low coefficient of friction. It could be much higher than that, um, and slow down the acceleration considerably more. So kind of interesting to think about. All right, example 13. You're trying to move a 500 Newton crate across a level floor. To start the crate moving, you have to pull with 230 newtons of horizontal force. Once the crate breaks loose and starts to move, so once you've overcome static friction, you can keep it moving at a constant velocity with only 200 newtons of force. What are the coefficients of static and kinetic friction? Okay, so a little bit of a twist here on our previous examples. Now we're not given the coefficients, but we are given the forces. So let's see what's happening. Here we have a crate. You're trying to pull it horizontally on this floor. So before moving and constant velocity are two separate parts to this example, right? So when we're dealing with something before it's moving, that's the static friction portion. And then once it breaks loose and starts to move, we'll look at that portion separately. So before it's moving, we have its weight, the force of gravity pulling down 500 newtons. We have the normal force from the floor, again, 500 newtons, because this crate is not moving up or down, just sideways. We are pulling on it with a force of 230 newtons. Now, based on my drawing, I have a little rope here, so I labeled it as a tension. You could label it as an applied force. It really does not matter, because it's not specified in the problem. So I just left it as a tension since that's what I had in my picture. And we have this static friction force, kind of holding it back to the left. When it's moving at a constant velocity, we have again the force of gravity pulling down. The weight of the crate did not change, so it's still 500 newtons. The floor is still holding it up with 500 newtons of force. Now, once it's moving at a constant velocity, we only need to apply 200 newtons of force. But now we'll deal with kinetic friction instead. Okay, so just before this crate starts to move, that means it's not moving yet. So its acceleration at that moment is 0. So that means the tension force and the static friction force are equal to each other. Right? So the static friction force is the static coefficient times the normal force. And we know that that's going to equal 230 newtons because that's the tension force that we're applying. So to find the coefficient, all we need to do is divide our tension force or our applied force by the normal force. So 230 divided by 500 gives us a coefficient of static friction of 0.46. Now, does this make sense? Well, potentially, right? It's a number between 0 and 1. So it could make sense. Let's compare it to our kinetic friction coefficient and just make sure that it really makes sense. Because remember, our static coefficient will either be bigger or equal to our kinetic coefficient. So let's take a look. After the crate starts to move, well, it still has an acceleration of 0 after it's moving because we're keeping it moving at a constant velocity, right? So there's no change in its velocity, meaning there's no acceleration still. Right, so we're thinking about not the moment that it starts moving, because obviously we'll have to speed up to start moving, but we're thinking about the time once it's moving at a constant velocity. So in our x direction, we again have tension minus friction, but now we're dealing with kinetic friction. So again, constant velocity, 0 acceleration means that those two forces are balanced, they're equal to each other. Now we have this kinetic coefficient times the normal force, and that's going to equal our applied force or a tension force of 200 newtons. So you can divide it just like we did before, and we get a coefficient of 0.4. Okay, so now this is still a number between 0 and 1, so that checks out. The kinetic coefficient is smaller than the static coefficient, so that checks out. And both of our answers seem to be fairly reasonable. Woohoo! We did it! Okay, so do you guys have questions yet? Okay, I have a couple more examples that I could do. I wasn't sure if we would have a chance to do them today or not, um, but I think we have about almost 10 minutes left, 8 minutes. So I'm going to go through at least one more example problem, so we don't get too far behind tomorrow. So hang out with me for a couple more minutes. We'll get through some additional examples. Okay, so here we go. This is a more advanced example problem, which is why I really wanted to make sure that we hit this, because it is different than anything that we've done before, but it is very typical of what you'd see in Physics 1. So here we have a car in neutral rolling down a hill that is inclined at 20 degrees. So we no longer have a nice horizontal surface that we're dealing with. Now we have this incline, and we'll see how this affects our both our free body diagram and the math and all that stuff. Okay. So my question to you then that I want you to quickly think about, what are the forces acting on this car? Hmm. Well, some of them should be obvious, right? We definitely have the force of gravity. Remember, the force of gravity pulls down towards the center of the earth, so it'll be pulling straight down. It's sitting on a surface, right? The hill. So we have a normal force supporting it. Remember, the normal force is perpendicular to the surface. So in this case, the normal force is no longer straight up. It's going to be perpendicular to the surface. So it'll be off at a little bit of an angle. We're not applying a force necessarily. There could be friction. We're not really told either way. So I left that in there as a possibility, right? Gravity pulling down, normal force perpendicular to the surface, potentially friction. Okay, drawing the free body diagram, there are a couple of different ways that you could do this. So I'll show you both ways because one of them makes sense visually and one of them makes the math much simpler. Okay, so here I'm going to establish our coordinate system. So right and up are positive. But we could also have a rotated coordinate system that is directed along the surface of the hill. So now instead of our typical, right is the x direction and up is the y direction, now if we take that coordinate system and rotate it a little bit, so that we can see that positive y is perpendicular to the surface and positive x is along the surface, that is also a totally valid coordinate system. Remember, you can set the coordinate system to be whatever is most convenient for you as long as you keep it consistent. So I'll draw both cases for the free body diagram. So in the first case where we have the traditional coordinate system, We have the force of gravity pulling straight down towards the center of the Earth. We have the normal force off at this 20-degree angle, right, perpendicular to the surface. And we have the force of kinetic friction along the hill, right? It opposes the motion. The motion of the car is going to be down the hill, so friction would point up the hill. And again, that would be at a 20-degree angle. Yeah, so this is totally valid, but it's not super convenient just because now we have two forces that are off at an angle. So we'd have two forces that we have to break down into their x and y components. You can do that. Absolutely. You have the skills to do that. It's just a little annoying. So what we could do is use this rotated coordinate system, okay, where in this case, you kind of like tilt your head a little bit. The normal force is straight up according to, sorry, I'm pointing at my screen, according to this positive y direction. Our normal force is straight up. And that would make our kinetic friction force straight to the left on this coordinate system. And now our force of gravity no longer points straight down, it's off at that 20-degree angle. So basically what we did is we took our normal free body diagram and we just rotated it by 20 degrees to get this one over here. But this is convenient because now we only have one force on an angle, one force to break down into its components. But again, either way is totally valid. Okay, what is the car's acceleration in the y direction? Well, 0 if we use convenient axes, right? This car is not it's not being launched into the air by the hill, it's not falling through the ground. So its acceleration in the y direction is 0. Okay. If this car is 1,000 kilograms and the coefficient of friction between the tires and the ramp is 0.45, what's the car's acceleration? Well, I'm going to stick with this rotated coordinate system just because I'm pretty lazy and I prefer to not do more trig than absolutely necessary. So I'll stick with this rotated coordinate system free body diagram. So according to this free body diagram, the sum of the forces in the y direction is the normal force minus this force of gravity in the y direction, and that equals mass times its y acceleration. Ha. So again, we have this fleshed out a little bit more, but here's a tricky thing. Previously, like in all of our other example problems that we've done together, the x direction, we've used the cosine, and the y direction, we've used the sine. That was according to those situations. This is a different situation. And if we look at the free body diagram that we have drawn, we'll see here that this y component is actually the side of the triangle that's adjacent to the angle. So this y component actually uses the cosine in this case. Bizarre. But if we can remember our trig identities, what cosine means, what sine means, don't get tripped up by things like that. Okay, so rearranging our equation here, right, because our y acceleration is 0, that gives us the normal force equals that mass times g times the cosine of our angle. And so that gives us a normal force of 9,209 newtons. That's not what we're asked for, so we're not quite done yet. Right, here's our result that we got from that.
Sorry, can you go back a quick second?
Yeah. I know, sorry, I went kind of quick on that slide. Let me know when you're ready.
All set, thanks.
All right, great. Okay, so there's our answer for the normal force. But we know it's not accelerating in the y direction, it's accelerating in the x direction. So let's look at those x forces. All right, so in our x direction, we have this little x component of gravity now, and we have this negative component of friction. Well, not component of friction, all of friction is along that x-axis. So when we plug in our trig identity for this x component of the force of gravity, we see that this x component is now the side of the triangle that's opposite our angle. So we have to use the sign here. Again, it's different than every other example that we've done so far. So our x component of gravity is mass times g times the sine of our angle. Our friction force is the coefficient times the normal force. And that equals the mass times the acceleration in the x direction. Well, we have all of those values now, right? The mass is 1,000 kilograms. G is 9.8 meters per second squared. Our angle is 20 degrees. Our coefficient is 0.45. Our normal force, which we just found, is 9,209 newtons. Again, the mass is 1,000 kilograms. And all we're left with is A. That's good, right? Now it's just plugging numbers into your calculator and simplifying the expression. When we do that, we'll find that the acceleration is negative 0.79 meters per second squared. Oh, sorry. Okay, we'll stop there for today because we've hit that magic 4:30 time. So tomorrow I have a couple of last slides to show you to wrap up chapter 5. We'll talk very quickly about air resistance. I'll go through some of those chapter 4 and 5 review questions that would make excellent test questions if I were a professor. Um, and then we'll be moving on to our next topic. So woohoo, we've almost made it. But I hope you guys have a great day, and I will see you all tomorrow.